and looking at the stars and the universe. We are just a tiny speck of dust in this big universe. In fact, modern technology, which makes us so powerful, actually shows us that in an even more brutal way.
Next up is a speaker, an astrophysicist, a headline-making human being who went to the edges of time and space. We heard last year Mark McCaughrean talking about the Big Bang and taking us through time there, through the JWST telescope. Now we're going to see how the Event Horizon was created, the Event Horizon telescope, and a human being who dared to dream, who had the audacity to think that he could image a black hole, these monsters in the sky for which we have no explanation and which consumes light, energy, matter, everything that we know is dovetailed into that and nothing comes out. This huge mystery where even light cannot escape. This is an astrophysicist who, as a little boy and then as an adult, launched a global sort of collaborative to capture an image of that. It made headline news 2 years ago. And just to give you a little bit of the audacity of this, that this black hole that they imaged is 6.5 billion times the size of the sun. It's 55 million light years away. It's 38 billion kilometers wide, and it sucks in all light. And yet, they took a picture of it. And this certainly will shift our idea of what it means to be human, because we've heard about biology, we've heard about robotics, we've heard about artificial intelligence, we'll hear about microbes and bacteria, but now we'll be told that we are also possibly made of stardust. But ladies and gentlemen, please welcome Heino Falcke, a headline-making, amazing astrophysicist who's also a pastor, and he's going to take us through a journey through time. Heino Falcke.
Thank you so much to be here today and take with me a journey from the Earth to the end of space and time. And that's what I want to take you on with some slides and some thinking about what it actually means to look at the stars. And that's something I think that humans have been doing from the beginning. We've been looking up at the stars and wondering what is out there. Even before we've understood what science is, we have done astronomy as the first science, the first human curiosity. Whenever the sun sets and this bright light in the sky in front of you disappears, you actually see much, much further. The darkness lets you see the width and the breadth of the universe. And people have been sitting there and wondering what's going on. And you see this reflected in the old songs and stories that we read in our scriptures and writings from many, many ages ago. And we'll quote a few stories and a few verses from the Bible, which is my background as a Christian, sort of been reading and reading about. The heavens declare the glory of God, the skies proclaim the works of his hands. So people were looking at the sky, looking at the heavens, and they were looking at something that is much deeper than just stars and suns. They were expecting something that goes beyond themselves. They were expecting some spiritual answers, perhaps. And they were discovering beauty. And that's something that we see much, much clearer today when we take technology. You see the beauty of the cosmos that's there. And then there's another, I think, important realization, and that's reflected here by a statement from the Apostle Paul. And I think that's perhaps one of the most fundamental and or history-changing thoughts that's behind this. And I'll quote this. For since the creation of the world, God's invisible qualities, his eternal power and divine nature, have been clearly seen, being understood from what has been made, so that people are without excuse. So what does it mean? It means that for Paul, looking at the things, you look actually deeper. You see something about what was there in the beginning. But it also means that the things are not divine. The things, the stars, the planets, are not gods. They reflect something much deeper. And so that enabled us actually to do modern science. Because we're not studying, looking at God directly, but looking at the stars, but we would be able to look at lights, we'd be able to understand them. And what they would show would reflect something that lies much deeper. For example, natural laws, the laws of science that we use today, are a very abstract and deep reflection of something that, makes our world today. And they speak of a certain order and stability of the world. Because as the world is changing, the laws of nature are still the same. And so is the belief that God is the same in the past, now, and in the future. So there is some stability underlying this world. And then comes modern technology. And we look at the world in a very different way. And as we look at the stars and as we go into space, look back at Earth, actually it changes our perspective of space and time. And it changes the perspective of who we are. And one of the most interesting realizations is that actually time and space are not fixed. They can change. So if you read one of these other old verses, 1,000 years in your sight are like a day that has just gone by, or like a watch in the night. 1,000 years can be a second or can be a day. And in fact, that is very true if we understand the theory of general relativity, the theory about space and time. That a second can be different in a different place, can be different for a different observer. Time and space are not absolutes, they are not fixed. And that was a fundamental change that Albert Einstein brought about in about 1915. Have you ever thought about space and time? What is space and what is time? Have you ever touched space? Have you smelled time? Can you change time? What is it actually? What are space and time? And the realization of Einstein and others is time and space is what we measure. We measure space and time with a fundamental ruler. And that fundamental ruler that we use today to measure space and time is light. And the true constant of the universe is not light, is not time, is not space, it actually is light. More specifically, the speed of light. The speed of light and the theories that we have in physics is always constant. Wherever you are, whatever you do, the speed of light is the same. And the speed of light is also the speed of information, the maximum speed of information. It's the speed of forces, the speed of propagation. The speed of light really rules the universe. And what is speed? Speed is kilometers per hour, length divided by time. So the ratio between length and time is constant, but length and time can actually change. And that was another revolutionary thought that Einstein had. And then there was another realization, trying to understand gravity. What is gravity? Gravity actually still is a deep mystery. It's a force that only has one direction. It pulls in one direction, and it keeps us on Earth. What Einstein said, actually gravity is able to change space and time. And what it does is actually that if you have a body like the Earth, it will actually bend space. That's what gravity is. It's bending of space. And if you then have light go around curved space-time, then light will go around a curve. It will follow the bending of space. But then, of course, space is stretched. Space becomes bigger. So light, which also is a clock, has to make bigger steps. So time is also stretched as you go around a body which has gravity. And so time and space change depending on how fast you go, or whether you are here on Earth or in space. In fact, if you use the navigation system, your GPS system, then you'll make use of the theory of relativity, because it measures arrival times of light from satellites high up there. And they have extremely precise clocks. But when you launch them, the clocks will go wrong here on the ground. It's because space is curved in a different way here than up in space. Once you launch the satellites, the clocks actually go perfectly right. So they change by 38 microseconds per day. They go faster in space than here on Earth. And you have to account for that. And without that, your navigation system would be off by 10 kilometers after one day. That's the effect that this has. Now, that's mind-boggling enough. Space and time are being stretched. But you can stretch and time to the most extreme you can think of. And that was discovered just a few months later by Carl Schwarzschild, who was investigating, now what if I put all the mass in just one little point? Today we call that a black hole. At the time it was just a mathematical curiosity, just a trick to make calculation easier. Nobody thought these things would exist. It was just, a little bit of mathematics. But what you would see is that if you have that configuration, light would actually be deflected so much, it would actually disappear in the deep funnel, which would be going would go to infinity. It would never be able to come out. So light would come to a stop. That means that actually time would come to a stop. And even space is no longer defined in this one point. And even before that, something strange would happen. There is this fundamental border, which we now call the event horizon. That's even before you hit this black hole, that there is no way for light to come out, which means not only light cannot come out, no information, nothing that happens inside will ever come out. And that is a deep frustration, but also a deep challenge for physicists. Because, in those black holes, you have the laws of the universe being turned upside down. You have the conditions that happened at the beginning of the universe in the Big Bang, in these black holes, but you cannot study them because no information will come out. And there's a part of our physical universe which exists. It's physics, but we cannot measure it. And what is physics without measuring it? And so it's an ultimate frontier of science and of our ability to understand and to learn. And that's why it was so shocking. And that's why Einstein said, that's a nice mathematical curiosity, but it cannot exist. This cannot be made in the universe. The universe doesn't make things like this. Oh, was he wrong? We learned in astronomy that the universe actually is changing and the universe is evolving. And what you see here is a beautiful dust cloud of little dust specks that were actually out there in the universe. And that's where we were born from. We were born from such a cloud of dust. And we learned that in the last 100 years. We do simulations these days in supercomputers, how the universe was evolving. And you see how, in fact, gravity plays out its fundamental role as the creative force of the universe. It pulls this dust together because all the dust particles attract. If everybody pulls in one direction, you can actually make stars. And that's what's happening in these clouds. And these clouds become smaller and smaller, the density goes up, the temperature goes up, and a star emerges and begins to shine. And that's how our sun was made, and that's, in this process, how our planet was made. And so stars are being born, and we still see that today, that stars are being born in the universe.
But we also know that stars have a limited lifetime. They come to an end. They will die eventually. And what you see here is the end of a star, which actually, before this star dies, will actually shed his outer layers. And that's important because the star gives back before he dies. Something I think we should also, as humans, think of before we go to our final stages. Because in the middle of a star, a lot of another creative processes happen. Under the pressure of gravity, under the heat and energy that was there, new elements were fused. Out of hydrogen, helium was formed, carbon, nitrogen, oxygen, all were made in stars. And now the star gives it back to the universe. And out of these dust particles, new planets will form. If you zoom in into such a picture, you see these little things that are there, which actually have the size, few times of the solar systems in width, and actually 10 to 100 times the length of our entire solar systems. And so the star has become dust. For dust you are, and to dust you will return. That's true for us humans, and it's true for stars as well. And if the star is really big, if it's really, really massive, it will die in a massive explosion. So I just wanted to wake you up, sorry. And so you have the outer layers being expelled into the universe, and actually heavy elements are being made. And in the very center, the core of the star is being compressed so much that its gravity overturns every other force in the universe. Nuclear forces, electric forces, no force in the universe. Even though they are so much stronger here, they're overturned and overpowered by gravity. So that core of the star becomes smaller and smaller. As it becomes smaller, gravity becomes even stronger. And it will never stop. It will collapse to a point. And we see that happening many times a day, actually, now in the universe with modern technologies and telescopes, which see supernova going off in the universe and the deep cosmos. And it creates spectacular light shows that you see, which actually really show the beauty. Death can be, have a beauty as well in the universe. And now we look further than just our own Milky Way. This is the Andromeda galaxy, 2.5 million light years away from us. It's a galaxy like our own. So we would be, rotating in this. And daily it would be somewhere, I think somewhere, up there. I don't have a laser pointer, but, we'd be rotating around the center of the galaxy in 200 million years with 250 kilometers per second around the center of that galaxy. That would be us. If we were there. And there are 200 billion stars, probably 1 trillion planets in there, and 100 million of little black holes which are circling around the center of that galaxy. And in the very center, you have a very deep concentration of stars. Well, we have here one sun, we'll have 1 million suns in the center of our galaxy. So the night sky will look completely different if you're in the center of the Milky Way. And you also have thousands, millions of little black holes. And they actually merge to form a supermassive black hole, a black hole that's bigger than anything we can imagine. And this is a picture of our Milky Way looking from the side, and you're seeing the dust clouds that actually block our view. We're now zooming in with telescopes, switching over to infrared vision. And infrared vision allows us to look through the dust, and we see this central cluster of stars, and these are images that my colleague Rainer Genzel and Andrea Guess in Garching and in Los Angeles made. And what you see there are the central tiny part of the galaxy with stars over 16 years. And you see how the stars actually move. The stars are not fixed. They're not fixed stars. They are moving stars. And every 16 years, this one star has an elliptical orbit, takes an elliptical orbit around something. And it moves with 8,000 kilometers per second. So if it comes down here, it moves with 8,000 kilometers per second, makes a turn, and goes around.
So if you take your, I guess, BMW now, and have an 8,000 kilometer per second going around on the highway trying to turn, you need very good tires, A, and secondly, in addition to that, you need a force that keeps you on the track, okay? And what force can that be? It's, of course, gravity in the universe. 8,000 kilometers per second. You know, the force that you need there is 4 million times than that of the entire mass of the sun, of our solar system. 4 million suns in one little point concentrated, where this star goes around. And what's there? In the optical and the near-infrared, you don't see much. You don't see 4 million stars. You see, you know, something faint. But if you go to radio, you actually see something bright in radio light. And so when I was looking in the 90s at this, I was wondering, you know, if there is a black hole really, is there a way we could see it? Can we see a black hole really? And how do you see a black hole? Well, you have to shine light at it. And what you would see is actually the light that disappears. So you cannot see the black hole directly, but you can see the shadow that it casts, the light that it absorbs. And today we're doing, you know, big supercomputer simulations, how a black hole would operate, and you see some of the simulations that we did in our group later on. And you see gas going around the black hole because it's orbiting like the stars around the black hole with almost the speed of light. The gas heats up to enormous temperatures, can become the brightest object in the sky if you just let matter fall towards the black hole. In fact, black holes can be the most efficient power sources in the universe. I haven't calculated for India yet, I must apologize, but if you have 10 buckets of water, you pour it into a black hole, it heats up, it can provide all the Netherlands for an entire year with all forms of energy, just 10 buckets of water, okay? That's how efficient black holes are in transforming matter into power, into energy, and that's what they do. Luckily, in the center of our Milky Way, only a little bit of matter is going there, like a fraction of the moon every year. Still a lot, but in terms of power, not enough to burn us here. And what you see is, next to this heat, to this light, you see the darkness. In the central region, this is a calculation on supercomputers which takes all the physics into account, how gas flows, how light is bent, how light is created, and how light is absorbed. In the very center, you see the darkness. The coldest spot in the universe is in the very center, surrounded by the hottest gas, the hottest light in the universe. So the extremes in black holes are really extreme. And what I forgot to mention, why is it interesting to physicists? Not just the extreme between light and darkness. It's also there where the two theories, the big theories of our world collide. Namely, theory of relativity, of space and time, and quantum of quantum theory, you know, matter and light. In our theories, that's the point where those two theories are incompatible with each other in current theories. And that's why we want to look at it. Not just understand why the energy is. This is a fundamental limit of our current physical understanding. If you then choose the right radio frequency to look at, you're actually zooming like with an X-ray, you're zooming into the region with a light that comes directly from near the black hole. And then that's what we predicted you would see. You would see actually light go around the black hole. In fact, there's a point when you stand above a black hole, you look forward, you would actually look around the black hole, and you would see the back of your head. Right? So that, because light is bent so strongly that my laser beam would be shot around, go in circles, and hit me on the back. That's what happen. And then if you go further, the light disappears. And so that's what you see, a ring of light and the darkness. And you can exactly predict how big it is. The bigger the black hole, the bigger that ring, the bigger that shadow. It's a very direct prediction. And we said, you know, in 2000, we had a paper that said, okay, if we take that technology that was emerging at the time, we'll be able to see the black hole in the center of galaxies, in particular this one, with a super telescope that allows us to see the shadow of a black hole. Now, what is this super telescopes? It's not just one telescope, it's many telescopes, because you need a telescope the size of the Earth. The bigger telescope, the sharper it can see. And so, if you want to see something that is the size of a mustard seed in New York, as seen from Europe, then you need a telescope the size
of the Earth. And how do you build it? Well, what you do is you take telescopes around the world, you combine them with digital technology, you actually store the light that they receive on physical memory, you tag it with atomic clocks precisely so you know exactly when the light arrives, you make a digital copy of the light, and afterwards, in the computer, you put the light together as if a telescope that would reflect light and bundle the light in the focus. And the bundling in the focus you do in the computer. You do a digital copy of the light, and you bundle, ray tracing you do in the computer. And then you get an image of what a telescope the size of the Earth would see. You're missing some information which you need to sort of take care of, but that's what you do. And so we put together a global collaboration of people around the world, and we had some of these telescopes here in Mexico and Hawaii, on the South Pole, in Chile, in Arizona, in Spain, with an actually international team from my group, but other groups as well. So I was in Spain because I had the best food of all the telescopes. That was my favorite telescope. So, you have some privilege as a group leader, you pick the telescope. And, but the others also had nice food. So anyway, so that's what you do. You take the data, and we did this first big experiment in 2017, and to my surprise, everything worked. The weather was perfect, all the technology worked. I mean, the weather has to be good around the world, okay? Not just in one place, everywhere. And the technology, which is very different telescopes, it also worked. I mean, telescopes are sensitive people, right? So, I mean, if you want to scare them too much, sometimes they misbehave and so forth, but they all cooperated. And it was a really stressful time. I mean, it was like 2 weeks, we were observing day and night. And so this was the team in Chile before the observations. This was after the observations, so that's... but it was great fun. I mean, we really had great fun in doing this. And then the great moment arrived. Well, in between, actually, we had to analyze the data. In 2018, I was one of the first to actually see that data. And it was just like, I was hovering above the ground for an hour, more or less. Well, not literally, but it was just in my mind. It was just, but then you have to pull yourself back down, because if you see something really exciting in your data, you have to be extremely suspicious as a scientist, okay? Because you do not want to see what you want to see. You have to see what actually nature tells you. And so if something comes out that you want to see, then you have to be very skeptical. And so what we did, we separated into different teams, competing teams that would look at the data independently, and then you would compare. And only if we all agreed and we found all the errors in our data reduction, we would agree and go on to publish. So this was a very tense process, but it was absolutely necessary because we only have one world, and we have to check each other. So that was an important aspect. And so we had the press conferences. This was in 2019, the first one in the big press room here in the European Union. I think it was the first big press conference in that room ever, and I had the privilege to show that image. And that's the image we showed. We were looking at, well, wait, it'll come. So we have the image. So we'll start now in Chile. Music from my son, who was making film music, actually. And we are zooming from now the high plains of Chile, where one of the telescopes was, into another galaxy that we, tried as well, and was a big present to us. And so it's 55 million light years away, and what you see is a big bubble of light, 250 million light years across. And all that bubble was inflated by this beam that comes out of the center. And while we zoom in, we came to the heart of all this energy and power, and we saw that. And that was the first ever image of a black hole. Some people sometimes say, oh, it's just a fuzzy donut. But it's a limit of what we can do technology. It's what a telescope the size of the Earth actually can give you. And it shows you not only the ring of light, and it shows you the darkness. It shows you where all the information actually disappears, where the light disappears, and how far we can go with our knowledge. And we have no theory that allows us to even go beyond this. This is how far we can go with our theories and our understanding. So it's really a fundamental, limit in space and time. Like, we have the beginning, the Big Bang, and this is the end of space and time, so to speak. And it was news everywhere. We had 4.5 billion people actually saw this image at the time in 2019. Internet was going crazy. Cats and black holes also. People had a lot of fun at the time. And I don't know. Sometimes I would like to see certain pictures reversed, I don't know, in the top right. But okay, so it became part of the photo collections of the Rijksmuseum in the Netherlands, in Amsterdam, and the museum, the MoMA in New York actually took the picture into their collection. This was a cheesy Christmas movie on Netflix this Christmas. So next to Notre Dame, the royals, you had the black hole image, and their exhibitions and so forth. So, it really, I think it's more than science because it inspired people. And people intuitively felt that's something special, something mythical, something that was just fantasy, suddenly you can see, okay? And that makes a difference. And, we are now trying to expand the Event Horizon Telescope. We're trying to go to Namibia, build a new telescope there, to have the network bigger. Because, in fact, we're missing Africa and we're missing India. So colleagues in India are also trying to build a telescope here to make this network bigger. And we're also combining this with outreach programs to actually capture the imagination of kids, make them excited about science and the universe. So that's what we're trying. And so that project is 80-90% funded. So if someone here wants to give this final 10%, be welcome, help us. There's still naming rights to be sold. And then last but not least, we look further into the universe. And what you see here is that also iconic picture of the James Webb Space Telescope. What you see here is, a little part of the sky that if you hold a needle up and you look through the eye of the needle, that's a part of the sky you're looking at. And in that eye of the needle, you see thousands, 10,000 galaxies. Each of these little specks that you see is a galaxy. Okay, so each of these little things has hundreds, 200s, billions of stars. It has the trillions of planets in there. Each of them has hundreds of millions of little black holes, has one big supermassive black hole. And so if you then look at how many needles you need to look at the entire sky, you need hundreds of billions of galaxies to do that. And really, if you look how many stars there are as many stars as there are grains of sand on our beaches. And even that deep feeling of how insignificant it feels sometimes is already known, right? As countless as the stars in the sky and as measureless as the sand on the seashore. Some of the statement from the old prophets. So people were wondering about what is it that I am? And, looking at the stars and the universe, we are just a tiny speck of dust in this big universe. In fact, modern technology, which makes us so powerful, actually shows us that in an even more brutal way. We used to know, okay, our surroundings and our Earth, fine, but now, using the telescopes, we see how small we are. Not how big we are, how small we are. And and then coming back, and the sun rises again, and we are ending our journey and, reflecting upon this. And also that is not a new question. When I consider your heavens, the work of your fingers, the moon and the stars, which you have set in place, what is mankind that you are mindful of them, human beings that you care for them? So that is a deep question, who are we? And I think the answer is that we have been given, and also, the poem goes on, we have been given an enormous creativity. We have been given enormous possibility to think, to ask questions, to be curious, to love, to pray, to think, to hope for the future. That's something that stars cannot do. And in us really is the entire history of the universe, the history of our human species, but actually, in fact, the entire history of the universe. Every bit in us has been made in stars. Every bit in us has been made in the Big Bang. That's all in us. And I think it's not the grandeur. It's really our questions, our hope, our love, our faith that makes us special. And I thank you for your attention. So now I'm waiting for our host to come. And
Thank you so much, Heino. That was absolutely brilliant. We're just going to have a very quick window of conversation because first Heino said he loves to chat.
Sorry, yes.
And that was just absolutely mind-blowing, Heino. I wanted to share one other quick data point with the audience, which didn't come across, is that they constructed this with, correct me if I'm wrong, 32 gigabytes of data per second, which is 32 and then many billion zeros and ones?
Yeah, every telescope records now with 64 gigabit per second, and we have sort of 8 petabyte data in one of these observations. And then we turn it into one little image of a few kilobyte at most. So that's really called data reduction, going from petabytes to, a fraction of a kilobyte actually in the end.
Again, to my very injured team from the console, just to take heart that this image took 2 years to render,
Yes.
So that's the amount of data they were processing. But
part of it is because some of the data was at the South Pole, and you have to wait an entire day, which takes half a month to get a flight back. So.
Right. So I know the other aspect of this thing is that doing this cutting edge science, you say, reinforces your idea of the divine. And you spoke about how biological death is itself a kind of event horizon. And it's very similar to you going to the black hole and seeing the end of time. Could you talk to the audience about that?
I once gave a talk about this, and there was an artist in the room, and she actually had, for a previous talk, she had actually made some paintings about the universe, which were, wonderful. And then I gave a talk about black holes, and I asked her, okay, are you going to make another drawing now or pictures now based on this? And she said, no, I'm afraid. It reminds me so of hell, right? So of death. And I said, wow, okay. But in a sense, that's true, because it's sort of a, it's the other side of physics. The one where you can jump into a black hole, you can experience what's inside, but you cannot tell anybody what you're experiencing there. And so it's a physical, eternity. It's a different place, even though it's part of our universe. And so that's an interesting part. But what is sort of what I feel looking at all these pictures, it's also the sense of beauty and stability that's underlying our universe. And I'm someone who believes in a God that's at the beginning. And so I always say, I think modern physics doesn't. The question is not, whether there's a God or not. You need a beginning. You need something that is sort of underlying everything. The more the question is what or who is God, right? So I think we should be talking about, what and who is God.
The first cause.
The first cause, right? What is the first cause? And it's, for physicists, it's just crazy. You go to the Big Bang, yes, but where does the Big Bang come from? Well, you have some ideas. Okay, but where do the laws come from that make the Big Bang or a multiverse? Where does it all come from? What is the first cause? And what is there when there was no time, before the Big Bang? And you just, physically with science, you just don't get an answer to this. And that's the other realization of modern physics, that we've been running into fundamental limits of our knowledge. The event horizon is one, the Big Bang is another one, but it's the speed of light, it's the chaos theory, the quantum uncertainty. There is nothing absolutely certain in this universe. You cannot, with absolute certainty, predict anything in the future because it is open. So there is a certain regularity, but there's also freedom in the universe and a limit to what we can know. And finding your way in this parameter space, I think, requires more than just science. It's a deep, sense of who you are and the face and, yeah.
Wow. That's, as I said, that's, even when we were chatting earlier, it's incredible and profound coming from you, Heino, because literally, I mean, no one can question your credibility, taking one to the end of time, and what you just said.
Actually, that's wrong. Everybody in science can question my credibility and should always question all my credibility. That's what science is. So,
it's amazing. You literally just cut me off before I said that one of the most profound things I took from your talk was that amazing thing you said, that when you had found this, which you've been searching for from the time you were a kid, when that idea first came to you, but you cross-checked it so much that you don't, play into your own confirmation bias. I think that's something we can all take into our lives, our everyday lives. But just coming back to this, Heino, the other beautiful idea you suggested, I don't know if it's a scientific truth, is that black hole could be a portal into a white hole, and that there's a bridge, a kind of wormhole, is all of that just fantasy?
That's definitely
or
not
does the maths play out?
Yeah, that's definitely not my idea. I mean, in fact, Einstein was one of the first to come up with this. So there could be a bridge between the black hole, which was the end, and the white hole, which would be the beginning. And you could connect the two. Mathematically, you can do this. But then the stupid physicist comes on, and the physicists have to decide which part of mathematics is actually reflecting reality and which one is not. And so far, we have not seen any evidence that white holes exist and that the conditions are right to actually create wormholes, because you need a certain form of matter that doesn't actually exist to do this. So I am very skeptical that we ever be able to travel through wormholes as much. I'm a Star Trek fan. I'd love to do this, and I'd hope to see this, and hope I'm proving wrong. But right now, physics doesn't give us a good hope to actually, find wormholes in the universe.
So just, Heino, we're kind of running out of time on this relative time on Earth. But so I wanted to ask you just this, that when you say that doing this level of science, you butt up against your own limits of knowledge, is that the only reason, like you also said about biological death, that it's a kind of threshold beyond which you know nothing. So that is a sense of divinity, just because you don't know what happens after that. But is that the real reason which reinforces your idea of the divine? Or are there like laws of physics itself? You said now about multiverses and all that, but are there laws of physics which show intelligent design or which just is inexplicable?
I don't think you can actually, and I would be very disappointed if you could prove God with science, because then God would be part of science, and it would become actually small and explainable. In fact, that's the discussion that happened at the beginning of the last century. Actually, the founders of quantum physics, and they were all sort of struggling with what is their picture of God and physics, and they were afraid that God would be, or thinking that God would be part of science. And I think it's beyond science; it's before that. So that's. And there's something that needs explanation, which we cannot scientifically approach. I think and you need to fill it in with what you believe, what you put at the beginning. There's a big question mark. And some people just leave it as a question mark, some put an exclamation mark there, some leave it blank. But something you have to deal with it. That's one thing, it's a philosophical one. And the other one is sort of this, the spiritual experience that people have, that have a sense there is something bigger than me. And that something bigger actually I can connect to, and it loves me. And that's another sense I do have. I think as humans, we are here, we can love each other, and the universe, and God loves us as well. So I think but I cannot prove that. There's no science that can prove this.
So just last question, because we're trying to catch up on time, Heino, is that, when you were a kid, you were playing in your backyard, and there was a wall which you wanted to see beyond.
Yes.
And you kept digging into that wall with your baby hands, and you could never get past it. And then when you grew up, you realized that you could actually walk around that wall, rather than dig through it. So the question is that when you're talking about the divine and doing science at this level, is it that it's a social training, because you're a pastor, you come from the Christian tradition? Is it just an emotional, sociological need? And how does that pan out in your scientific community,
Yeah.
Are you kind of, do you keep it under, I know you don't keep it under wraps because you've written about it and you speak of it, but how do other scientists respond to that?
Yeah, no, I think astronomers are special because we are exposed to the grandeur of the universe and to the beginning of space and time. And we know, and we have a tradition that goes back thousands of years, right? So I think we used to know that, the universe is more than just, just the stars. So that's, I've never had any personal problems. Sometimes when people make a joke, I make a joke back, and so I think we're, and we chat about it. But I think, looking at the stars, it always raises spiritual questions. And even atheist colleagues of mine, when they give a talk like this, it feels very spiritual to me, even though they don't say it, right? So, and it's almost unavoidable if you do this. And it's good. I think we should be doing this. We should be doing our science. We try to make the world better, but we should know that there's, something deeper, and actually reflects, our questions, that we are curious. We want to know. And that's, again, what we are as humans. We want to know. Let's ask questions, and let's even think beyond. And let's not be limited by those walls, and hope that there is more than just the things that we see. It's a hope, but we should always have and keep the hope.
Thank you very much, Heino. Again, reading from your book, I guess I knew of it, but it comes in as a distillate that it's not just Heino, but Galileo and Copernicus and Kepler and everyone, who really pushed the boundaries of science.
All the big minds were actually thinking more about just the universe. They were thinking about God and what it means and so forth. So I think science is a very, it's a broad topic. You cannot just stop at this wall. You need to think, beyond.
Thank you very much, Heino. That perspective about being human, this is an important one. Thank you very, very much for being here. Thank you. That was so good, so good.